Yes, very good afternoon, everyone. Am I audible clearly to you?
You are audible. Please share your screen.
Okay, sure, sure. Yeah, yeah. Is it visible properly?
Yes.
Okay, sure. Yeah, so good afternoon, everyone. First of all, I would like to thank all the organizers of PKI 2023 for giving us this opportunity to present our research paper entitled FPGA Implementation of AES Algorithm with Lightweight LFSR based approach and optimized key expansion. Me and my colleague Vaishnavi Deshpande are present over in this conference to present this paper. So I'll just go through the agenda of this presentation. First, I'll introduce and explain the motivation behind this topic, the literature survey, objectives, methodology, then the experimental setup, results, and references. So first, in today's world, in the world of IoT, in the world of edge computing, the security of the data is very basic necessity. The cryptography is necessity of communication and data exchange when it comes to confidentiality and integrity. So we choose the advanced encryption standard, that is AES algorithm, which is a cryptographic symmetric algorithm widely adopted due to its robust security and resistance to various cryptographic attacks like brute force attacks, etc. So our work proposes an efficient implementation of these AES algorithms. There are three types of AES algorithms: AES 128, 192, and 256, which are based on the size of the key used in that algorithms. So we propose efficient implementation of these three algorithms on Intel DE10 Lite FPGA development board. Why we use FPGA development board is to promote or to get the advantage of hardware cryptography. So in this work, we are proposing LFSR based approach to do the substitute byte stage in the AES algorithm, which I'll explain in further slides. Additionally, we are proposing a round-wise key expansion algorithm, which will be for storage efficiency throughout the AES algorithm. So as you can see in this table, these are the three AES algorithms: 128, 192, and 256. Their corresponding key sizes, their number of possible keys are given, which is a very large number and which is the robust thing about the AES algorithms. So throughout the literature survey, from starting with the comparison of the old data encryption standards with AES, then getting to know about various AES algorithms, the uh, the mathematics behind them like Galois fields and finite fields, etc. Getting polynomial arithmetic in our study, then going to the lightweight cryptography solutions, which were there proposed by some authors about AES algorithms, and finally implementing it on the hardware. This was our journey throughout this research. So the objectives are three. First of all, efficient implementation of AES algorithms on FPGA board. Then to get the advantages of hardware cryptography. The second one is trying the LFSR approach and validating it for the AES algorithm in the substitute byte stages. And third one is trying optimized round-wise key expansion algorithm for runtime key generation. In conventional AES algorithms, the keys are generated at first and they are stored in the device, and then they are used throughout various rounds, which you can see in this flow diagram. But we are proposing to get this key at runtime. At when the round starts, we are generating the key. So these are the three objectives we have. The proposed methodology is basically compromises of two main aims. First of all, LFSR based substitution bytes algorithm. So we all know that AES uses SBox for the substitute byte stages. So we are not using the and that SBox is basically stored in the device as an LUT. So we are not using that LUT. We are trying to generate that substitution to the input byte at the runtime. So for that, we studied the AES algorithm first of all, and in the original proposal of AES, Randall used particular irreducible polynomial, which is x raised to 8 plus x raised to 4 plus x cube plus x plus 1. And for when we come to LFSR, LFSR is basically a linear feedback shift register which is built up on a polynomial. So the primitive polynomial is used to generate this LFSR, as primitive polynomials give all the states which are present in this finite field of Galois field 2 raised to 8. So we chosen the primitive polynomial x raised to 8 plus x raised to 4 plus x cube plus x square plus 1. And while so basically our input is in this field x raised to 8 plus x raised to 4 plus x cube plus x plus 1, and we have to shift it to this one, so the primitive polynomial field. So for shifting we used isomorphism mapping, which you can see in this diagram. And by doing the isomorphism mapping, we converted our input data into different field which is given by primitive polynomial, and then we ran two LFSRs basically, which will be checking in the runtime, and at the end we will get the multiplicative inverse basically. So in SBox there are two steps: multiplicative inverse and affine transformation. So for multiplicative inverse we are using these two LFSR, and we are getting the multiplicative inverse of our output, input in finite field GF 2 raised to 8 using these LFSRs. So I would like to explain the theory behind multiplicative inverse and why the LFSRs are being used for finding the multiplicative inverse. So for 8-bit LFSR generated by a primitive polynomial, these are the equations which I have written. So s of t plus 1 is equals to t raised to 1 s of t, where t is the LFSR transformation matrix, and s of 0 we can see the initial seed to LFSR, because if LFSR is totally 0 at the start, it will never do any operations, or any XOR gates will be operating. So we have to give initial seed to LFSR, and currently it is 1 in our case. So in LFSR we know that every repeating every 2 raised to n minus 1 states, it gets the initial state back. Okay, so it repeats the cycle. So I can say 2 raised to n minus 1 is the total cycle that the LFSR can have. So while uh, while calculating the multiplicative inverse, we can see that we can say s t 2 raised to n minus 1 is equals to s of t. So when I power t to the 2 raised to n minus 1, s of t is equals to it again become s of t, that is the initial seed. And hence I can say that t raised to 2 raised to n minus 1 is the identity element, and we get the identity element in a finite field when one particular element is multiplied with its inverse basically. Okay, so I now suppose that when a LFSR has the input byte term in it, so that cycle might be, I'll call it as p. So we have to find the multiplicative inverse of p. So s of p is equals to t raised to p into s of 0. Now we have to find, so basically the multiplicative inverse of s of p is totally dependent on t raised to the multiplicative inverse of t raised to p. So finding t inverse of t raised to p can lead me to 2 raised to multiply it with 2 raised to n minus 1 minus p, the power to the t. So I can say that s of t raised to s of 2 raised to n minus 1 minus p will be the multiplicative inverse of s of p. Thus, in this way, we can find the multiplicative inverse of any element by using the two LFSRs. So we have proposed this approach, and we have implemented in the FPGA module in System Verilog. The next methodology is optimized round-wise key expansion algorithm. So as I said, in the conventional algorithm, the keys were generated at the start of all rounds, and then it were used in particular rounds. So it consumes lot of memory to store all the keys. In fact, we found that AES 192 and AES 256 doesn't fit on that FPGA, as a lot of memory were consumed by the storage of keys. So to idea is to generate the key at the start of every round, just prior to the requirement, and then reduce the memory storage consequently. So we propose this algorithm, and we so this algorithm basically means that we are generating every byte of key, and we found how to generate that byte of key at the start of the round, and this is the summary for that algorithm. The next is experimental setup. So basically what we did is we took two FPGA boards, Intel DE10 Lite FPGA boards, and we connected them to the two host PCs. One host PC will be sending key and the plain text to the FPGA board, and that FPGA board will do encryption, whether it will be using AES 128 or AES 192 or AES 256. Then the encrypted data and the key will be transmitted to the second FPGA using UART protocol. In the second FPGA, to validate the decryption part also, we did decryption algorithm on that FPGA. It can be again AES 128 or 192 or 256, and then that FPGA will again send the data to another host PC, which will be the original data that we sent through one host PC, right? So in this way, we validated the encryption as well as the decryption part. In the results and comparison, we found that basically, as you can see in these two tables, one is for decryption and one is for encryption. AES 192 and AES 256 couldn't, the code dump couldn't fit on the FPGA board with the conventional key expansion and SBox based AES algorithms. So when we implemented the proposed AES algorithm with LFSR and key expansion, you can see that for AES 128, the device utilization, I can say, reduced from 93.5% to 31%. Same case about encryption, it reduced from 91% to 29%. In AES 192, 34% was the device utilization with the proposed algorithm. For encryption also, it was 34, and for AES 256 the decryption took 40% and encryption took 39%. So the result was good. It reduced the complexity of routing, it reduces the device utilization, the number of registers required, because storing the LUT is much about the registers and all. So this was the result. The device utilization was much reduced in the proposed algorithm. So these are the references. The book by Stallings about cryptographic algorithms was much helpful for us throughout this journey. So I would like to thank all the chairpersons and all the organizers for inviting us. I would like to know if anyone have any questions, please.
Any questions? No. Thank you, Samruddhi.
Okay, thank you so much.
So
Student.
our